Welcome back, everyone. We'll begin our afternoon session. Hope you had a great lunch. I am honored to introduce Professor Varun Gupta from Northwestern University. He'll be talking about greedy algorithms for multi-way matching with bounded regret. Okay, the talk will run for about 50 minutes, and feel free to ask any questions. Over to Varun.
Okay. And I'll also ask questions, so please feel free to answer. I mean, you should answer when I ask the question. Okay, so broadly, this talk will be on stochastic control of queuing systems, a little bit like Professor Iyengar's talk in the morning and also Siddharth Banerjee's talk yesterday. So you see uh, themes that you've seen earlier emerging again in today's talk. And this paper has an interesting story, which is I haven't worked in this area before until this paper. I was reading a different paper by a set of authors, which I'll mention in the talk, and based on something I had done earlier, I knew I had a slightly better algorithm than what they had done, which I thought must be known. So I was feeling embarrassed when I realized it wasn't known, and I was trying to write that short result up. But the paper kind of grew while I was working on that write up, and I'll sort of say a little bit about like how that work broadened as the talk goes on. Okay. So like I said, the talk will be on sort of theoretical control of a queuing system, but let me just begin with like one motivating application for why we're studying this question, and that comes from these paired kidney exchanges. Okay, so if you haven't seen what these kidney exchanges are, the way it works is that there's a patient who needs a kidney transplant, and they may have a relative or a spouse or a friend who would like to give their kidney to their friend, but they're not compatible. Okay, so this person can't give the kidney to this patient. So they go to a kidney exchange where there may be one more pair like this, where there's a donor who can't give their kidney to the recipient, but the donor in the second group may be compatible with the recipient in the first, and the donor in the second on the first is compatible with the recipient in the second, right? So they can do a kidney exchange. Okay. By the way, there's a bug in this picture. I don't know if anyone spots it. That's just to check if you're awake. Sorry? Yeah, exactly. Good thing. So you're awake, right? So this is how I will draw this, right? So there is a purple type, which is a type of a recipient and donor, and a directed arrow means that the donor in the purple type can give their kidney to the recipient of the yellow type, and similarly, the donor of the yellow type can give their kidney to the recipient in the purple type. No, exactly, right? So again, there's no reason why you have to restrict yourself to pairs. You may also have a three cycle, right? So the purple person can give to the yellow, yellow gives to the green, and green gives to the purple, right? So it's sort of you can have like even longer chains. So I think there's some, I think people have done up to 6 cycles of length 6. It becomes harder because you have to do all these operations together in a given hospital. So it's sort of, you can't have very big cycles, but people have gone at least up to 6. Okay. So at a high level, like what would a problem like this look like? So you'll have some sort of compatibility graph between the types. So again, here a big circle is a type of a recipient and a donor, and there's a directed cycle or directed arc showing that the donor of one type can give to the recipient of the other. Okay. Uh, at any point of time, you'll have some queue of patients who are waiting in each type, right? So this basically says that there are 6 donor recipient pairs of this type waiting to get matched and get removed from the queuing system. There may be some rates at which further these pairs arrive into my exchange. And the high level question is, how should we execute these matches, which are cycles in this compatibility graph in real time, so that you maximize the match quality? So, I mean, I have an edge, which is compatibility, but there may also be some quality of the match, which is a better match or sort of a worse match. So you want to execute matches of high value, but you also want to minimize how long people wait in the system until their match, right? So that's sort of the high level question. So they're called angel donors, and what they do is they start a chain, which is they can give to, for example, so there's a 3 cycle here, right? So this person, so the angel donor can give to the blue person, and now what that does is you don't have to execute all the matches at one time, because now this So, right. So basically, kidney exchanges have been trying to look at how to offer incentives to encourage angel donors, where if you give a kidney today, you have a friend who will need a kidney like later on. I'll give them priority in the queue in for receiving an organ. So they're trying to create these kind of incentives. Yeah. So I think in Turkey, definitely they're trying to set up these kinds of incentives. So those are, yeah, so those are cadaveric organ donors. So that also happens. But even like angel donors also just give their kidney without any sort of expectation of getting a kidney immediately in return. But they're trying to create incentives. So this is again not my areas. I'm sure someone knows about this more than I do. But yeah, so it's a fascinating, I think, area of research just in terms of, from a healthcare side of view, incentive side of view, but also stochastic control side of view. A node is so uh, a donor and a recipient type. So the type, so there's something called like HLA typing, for example, for these organ transplant, which basically say like what's your gene profile, blood group, and so on. So each circle here is like one type of a recipient and donor. It's how many people are waiting off that type in my exchange who have not been matched and removed from the system. Exactly, they have same profile. So all these four people have the same profile, which is this one. These six people have the same profile as this green one. Good question. Thanks. Other questions? Yeah. Yeah, exactly. Each square is a pair. Correct. So the edges are among the types. So if there is no person in the queue, then I mean the edge exists, but again I can't execute the cycle because there's no person to sort of complete the cycle. So I can only complete a cycle if there's like at least one. So like this three cycle I can only execute if there's at least one person in each of these queues. Make sense? Okay. Graph edges don't change. Yeah. No, I will not. So again, this is just like motivating application. I'll abstract it to some sort of just proper just queuing control problem. I'll just assume it some has some value. Each cycle has some value or some reward. Correct, exactly. And also like if the donor is younger than the organ, the quality of life, they have this quality adjusted life years will be better. So again, depending on the donor type, the value will be higher. Correct, exactly. Yeah, so we're getting there. Exactly, it's like a classic queuing control problem, which I was, yeah. So that could be one more feature which tells you what the type is, right? Because if I am closer to, correct, exactly. So that's right. So like in correct. So like in, it's possible. It's like in US, for example, they have these regions which pool organs. But even within a region which can pool organs, it may be better to match someone who's closer because the organ spoils. I mean, if I'm carrying the organ, but which, I mean, in this case, I wouldn't. But if you were carrying an organ in a sort of cool box, ice box, it won't spoil as much. So all those things are possible. I mean, this is not an applied paper, so they're nice questions, but yeah. So what's the question you mean? Is that what you mean? Like, so there's just it's a source, but not it doesn't have an incoming arc. So, for example, if there is a vertex, that should be an incoming. Yeah, I mean, yeah, that's true. It should always be part of. So if there's no incoming edge, then they don't get anything from joining a kidney exchange, right? So then they just look for a cadaveric donor or angel donor or something like that. So donor here can give kidney to recipient here, donor here can give kidney to recipient here, and donor here can give kidney to recipient here. Yeah, exactly. Think of the kidney moving, not, yeah. Other question? Yeah, I'm coming to this model. One second. I mean, yeah. So okay, let me just jump right. So here's sort of the abstract model. So now I'm moving away from the application and sort of looking at a generic problem which captures the problem that I just showed you. It's called multiway matching problem. So here I'll think of some resources which are arriving into my system. So to map it to the problem that we just saw, a resource would be uh, a resource type would be a type of donor recipient pair, and this lambda I says at each time step what's the probability that a pair of that type arrives, right? So there, that's the arrival process. On the other side, I'll have some matching configurations, right? And the dollar dollar basically says that this sort of configuration has some reward, and there is some compatibility graph, right? So essentially, what this says is that I can combine a resource of type 1, resource of type 3, and I'll get some reward. Similarly, if I look at this configuration, this requires 3 resources, one of type 5, of 6, of 7, and then gets me some reward, right? So these are the directed cycles from my previous graph. So that's how I go from that to just a problem where I have resources and I have configurations where I can combine multi-sets of these resources and get some value. Okay. We'll study this problem in a discrete time setting. There's a horizon capital T. I have these resources. I'll assume there are n resource types. The resources are infinitely patient. So once they arrive, they can stay in the queue forever. They don't disappear, unlike Garud's talk this morning. For now, I will assume that the demand distribution, this lambda, the arrival probabilities are stationary, okay, and also known. So known, I will assume, but also stationary for now. So that now makes it a MDP because there's a proper stochastic process through which arrivals happen. Um, I'll assume that these matching configurations are fairly general. So I'll denote the configurations by this resource consumption matrix M, right? So this is the number of resources types times the number of matching configurations, where the entry MIM says for the configuration M, how many units of resource I do I need, right? So in the kidney exchange application, in each configuration, you'll just use one, at most one resource of each type. But again, you can have a generic problem where you combine 2 resources of type 1, 3 of type 2, and so on. Okay? And then R sub m is the reward. And I also want to model the setting where I can just discard resources, right? So someone comes to my kidney exchange, I just tell them right away, you know, I don't think I'll be able to help you, just go somewhere else, right? So that's what it says that I can discard resources. So I'll also have these configurations which have just singleton resource and 0 reward. So that's basically saying that I can discard these resources. And there are many metrics that I could try to optimize, but we want to maximize reward, but also keep the queue small. So for us, one reasonable metric is what's called the anytime regret, which says that at time t, I look at what's the reward that the optimal in hindsight is getting until time t, that's opt sub t. I see what is the total reward I have received until time t. The difference is the regret at time t, and then I look at the max of this overall t, right? So in some sense, if I just wanted to maximize reward, I can keep all the jobs in the queue, match them at the terminal time. I want you to stop you from doing that. So what I do is I say that at each time t, the reward should be close to optimal. Now you can't just keep jobs in the queue to maximize reward. Okay. So far so good. People okay with what we have so far? Exactly. Otherwise, you can't even solve exactly in n. Yeah, exactly. Exponentially many. That's right. Yeah. Yeah. Good. Arrival process and if there's any randomness of the matching process also. Good, good. Okay, so it's a discrete time problem, and each step only one item of some resource arrives. So the lambdas that I wrote, I mean, they should sum up to 1 if I entered them correctly. So just think of like it's a probability distribution over which resource arrive at each. Right. So I exactly. So another possible metric would be where I look at a holding cost and I optimize the max value of match minus the holding cost. So and that will make a proper MDP problem. I'm not doing that here, partly because the algorithm that we have sort of gels better with this objective. But that's a perfectly reasonable metric also. Yeah. Yeah. Our question. Okay. So for now, let me just sort of throw the problem to you. Correct. Good. Yeah, let's get there. Okay. So now before I sort of start discussing my results, just sort of want to throw the problem to you, which is what might be some initial ideas for how you can run this queuing system, right? So Rahul has one sort of suggestion, which is, since I don't have holding cost in my problem, right? Jobs can stay in the system forever. One possible policy is I wait until the terminal time t and then just find the max weight matching. What goes wrong with that policy? Right. So if I look at just sort of the max regret, if I look at t over 2, I have gotten zero reward so far, right? So that will sort of be bad for this anytime regret view. That's okay, right? Okay. So what might be like a slightly better policy? I can't wait until the end. Good. So one thing I can do is every few periods I clear the market, right? And that was in fact like one of the policies proposed by this paper that I was studying, right? So it's a paper by Suleiman Kerimov, Itay Ashlagi, Itay Gurbich. They had a policy where every few time steps they'll look at the current queues and find a max weight matching. Okay. And the main result in this paper was that if you set the period between when you clear the market appropriately, it keeps the queues bounded, right? Um, the downside with this result is that the performance is very sensitive to the time period that you choose for how you clear the market. Okay, so here's a plot from their paper where they have the same queuing system. In the left plot, they're clearing the market every 5 steps, and as time goes on, the suboptimality grows linearly. Instead, if I clear every 10 steps, which is like just twice, it's not like orders of magnitude larger, my regret is bounded. Okay? So it's sort of very hard if you just look at this picture to figure out what should be the right period at which you should be clearing this queuing system. Okay? So again, works if you can figure out this period correctly, but sort of this is a tunable parameter which is not easy to set. So the reward matching, right? Max weight. So there's a weight for every configuration. Yeah, so multi-way match. Exactly. So you're saying it's NP hard or something to do. What may be also enough is you solve the fractional matching and just round it down. I don't think you lose too much because you're okay with constant regret anyway. Correct. Exactly. Exactly. Yeah. Yeah. So this policy will have some stationary distribution. That's true. I mean, it's periodic. So it's, I mean, if you just sort of look at the epochs where you're clearing, I think that embedded chain will become stationary. Yeah. Um, Question on this policy? This seems okay to people. Okay. All right. What else could you do, right? So there was one extreme, which is wait until the end, match. There was some in between thing, which is wait until some time steps and clear. Like, what's the other extreme? So you mean like based on how many jobs have accumulated? Uh, I think it's still unclear to them also and to me also, which is how should that be set? Uh, and that's sort of the main problem, which is, I mean, this policy works nicely if you can figure that out, but we don't know how to set that. That's sort of the problem. Right. So what's the other extreme of like waiting until the end? So if there's any match that you could execute, just do it. Like, so that's the greedy policy. Okay. But you can't just do greedy because you may be executing matches which are just bad. So essentially what greedy here says is that you sort of first solve like this planning problem like Garud was doing today, which says, okay, in the optimal fluid solution, which configurations you would actually be using. And within those configurations, if there's anything you can do right now, you do it. Okay. What they prove is that this works, but only if all the configurations are of size at most 2. So if any configuration has 3 items, then this policy doesn't work. Okay, so that's sort of one downside of this greedy policy. Okay, but again, the good thing if this policy would work is that it has no parameters, right? There's no sort of clearing period. You just do it whenever you can. So one punchline of this paper is that if you just sort of change your view of what greedy means, then a greedy policy is optimal. Okay, it has changed here, but not there. It's waiting for this to sync. So when I say that you clear, I can only clear the jobs in the queue. So my policy in terms of when I clear doesn't depend on the queue. But what I do at those clearing periods is basically saying I have some current inventory of each type and I have some reward for each configuration. So I find how to clear those queues. And yeah, that's I think what Professor Sen was saying also. But we don't know how to do that in a better way than just statically clearing after every some period. I think this is just connecting. I think maybe just Wi-Fi. Oh, I see. I have to share. Right. Good. So here's basically what I was saying. So the punchline of this paper is that this greedy policy, which clears as soon as you can clear something, is not optimal. But if you just sort of view greedy differently, where you just greedily commit items when they arrive to a configuration that I will use them in eventually. Okay, so you don't sort of match right now, you wait to match, but you just commit resources to some configurations when they arrive. That works. And again, this will become clearer what I mean by this later on, but that's sort of the punchline of this work. Okay. Um, Again, waiting to sync. Okay. So here's sort of the main contribution of the paper, right? So the first one talks about like what I mentioned earlier, which is I was initially planning to write a paper only on this kidney matching problem, but it kind of grew. And what we can show is that there's sort of a more general umbrella framework of multiway matching, which incorporates not just the organ transplant matching problem, but many other resource allocation problems that people study in operation research. For example, network memory management, queuing systems, assortment optimization, bin packing. Okay. If I have time, I'll mention what this umbrella framework is, but even if I don't get there, it's fine. Uh, and what we can also do is because we have this sort of greedy algorithm which works for this umbrella framework of matching problems, we have an algorithm which has small regret for all of these other problems for which people have very different looking algorithms. Okay, so one algorithm kind of works for all of these different applications. Uh, and in terms of techniques, it's basically very basic techniques that people in stochastic community are familiar with, which is Lyapunov drift. But we combine it with a technique that people use in CS, which is amortized analysis, to handle non-stationary arrivals. So we can go beyond just stationary arrivals because we have a very nice greedy policy and analyze what it does, even if I have non-stationarity, right? So that's like technically, I think the most interesting part of this paper, the non-stationarity bit. But I don't think I'll have time to get to that result. Okay. So here's sort of the outline. I'll begin with this organ allocation problem, and I'll say what the greedy algorithm is and sort of how do you study the regret for this policy. If I have time, I'll say how we can extend that to non-stationary arrivals, what this umbrella framework is, and then sort of what the results are. But even if I just do the first bit, I'll be happy. Okay. So to discuss the results, I have to first give a few definitions. The first thing that's important is something that we've seen already in Professor Iyengar and Siddharth's talk, which is a planning problem which sort of broadly tells us how to run this queuing system optimally in a fluid sense, right? It's called the static planning problem. It's this very simple linear program. We have a decision variable x sub m for each matching configuration, which stands for what's the rate at which I execute matches of configuration m, or in a fluid sense, right? So my objective is I want to maximize my reward based on these decisions. My constraints say that for every resource I, the rate at which I consume them, which is I match them with in configuration m times how many resources of type I are in configuration m, that should be exactly equal to the arrival rate of that resource. Okay, and it's equality and not less than equal because I'm assuming I also have the singleton configuration. So I can always use singleton configurations and remove items. So that's why it's true with equality. So this is sort of this planning problem, which we have seen this morning as well. And this sort of condition under which we can get order one regret, this basis robustness condition says the following, that if I have some optimal basis for this linear program, an optimal basis just means the configurations for which my decision variable is non-zero, okay, then if I perturb my arrival probabilities, lambda, within some ball of radius epsilon to lambda hat, right? So I sort of slightly perturb my arrival probabilities. Then for this new arrival rates, I can find an optimal solution again with the same basis. So my basis is robust in that sense. I perturb my lambda a little bit, my optimal solution can still be found within the same base. Okay. So if this condition is true, then it's called the general position gap with epsilon. And I'll say on the next slide why the word general position gap. But this is the condition under which we can get bounded regret with our greedy policy. Okay. On the next slide, I'll try to convince you that this condition is fairly mild. We should expect this to hold very generally. And to convince you, I have to sort of frame this condition in a slightly different manner by using the dual of this static planning problem. Okay. So an equivalent way of stating this general position gap condition is that my arrival rates satisfy this condition if when I look at the dual to the solution to the dual of this problem, it's unique. And also if I perturb my lambda to some lambda hat within this epsilon ball, then my dual remains the same. Okay. And with this condition, it's easy to check that this condition should be true fairly generally, because here is my dual problem. Okay. So in my dual problem, the decision variables are some value for each resource. I'm trying to minimize the expected value of the resources. My constraints say that in any configuration, the value of the resources is bigger than the reward I get from that configuration. Okay. The main thing to notice is that this set of constraints does not involve the arrival rate. So I can just think of the feasible set of my dual as some polytope. And I'm trying to find a solution in the direction of lambda high that minimizes in the direction of lambda. So lambda is some direction, but now you can see that if I sort of pick lambda randomly, most often I will end up at a corner of this polytope. So I'll have a unique solution and it should be robust even if I perturb my lambda within some ball, right? So that's why it's called the general position gap, because if I pick lambda in a general position, then I have this uniqueness condition. And the theorem that's true is that if this is true, then the greedy algorithm, which I'll show you on the next slide, has bounded regret, which grows as cube in the number of item types and as 1 over epsilon in this gap. Questions so far before I mention the algorithm on the next slide? That's true, I think. Is it true? Exactly. With primary, it's not quite clear, but dual seems more testable, right? Okay. So on the next slide, let me tell you what this greedy algorithm is. It's going to be very simple. Okay. So what we'll do is, let's say this is a very simple instance. I have 3 resource types and I have 4 configurations, some reward for each configuration and some compatibility graph. And for now, imagine that the entries in this resource consumption matrix are either 0 or 1. Okay? So the first step that we'll do for our greedy algorithm is we'll solve for an optimal solution for the static planning problem. Let's call that X star. And then any configuration which is not an X star, we just ignore it. Okay. So in this case, let's imagine that only these 3 configurations are part of my uh, basic feasible solution. Okay. Now we will only execute matches of these 3 types. That's like one thing we will do. Okay. And the way we will run our queuing system is that whenever a resource arrives, that's the key idea, we'll commit it to some configuration in this basis greedily. And I'll tell you what greedily means in a bit. Okay. The way we commit the resources on arrival is we first maintain for every configuration a queue of the resources that are part of that configuration. So for example, this red resource is part of both the first and the second. So I have separate queues for it for these 2 configurations. So they'll be waiting to be matched. And you'll see that for every configuration, one of the queues is empty. Otherwise, I could have executed a match, right? So one queue is empty for each configuration. Okay. Let QIM denote the number of unmatched type I items waiting for resource I in configuration M. Now for each configuration, I'll define a potential function, which is this cyclic sum of squares potential function. Okay. Now let me walk through this slowly a little bit. Okay. So what I do is I'll look at all the resources which are part of this configuration. QI1M says how many resources of type I1 are waiting for configuration M, divided by this resource consumption matrix, which says for one match in configuration M, how many resources do I need of I1? So in some sense, this ratio says that if I was only constrained by type I1 resources, how many matches I could have done of this configuration. Okay? I just sort of pick any permutation of the resources, look at the differences, and then square it. Okay? That sort of basically tells me how imbalanced my current queues for this configuration are in some sense, right? So just an example, if I look at this particular configuration, what will be this potential function? I have 2 jobs for red, 3 for blue, so it's 2 minus 3 square. Then 3 for blue, 0 for purple, so it's plus 3 minus 0 square, and then 0 for purple, 2 for red, so 0 minus 2. Right? That's sort of the sum of square potential function. And now what do? I basically, whenever a resource arrives, I send it to the configuration so that this function drops as much as possible. So I want to, again, create balanced queues. So just an example, suppose this purple job arrives. I can try to figure out what happens if I send it to the last configuration. So how much will my potential function drop if I send it to the last configuration? Like, so what's the value of this potential function right now before I send the purple job? 2 square plus 2 square, so 8, right? So because I'm doing a permutation, right? So it's currently 8. What will happen once I send it to this configuration? Well, I'll execute one match. So I have to be sort of mindful. Okay, once I send it, I'll have one purple here. So I can sort of do one match, they go away. So then it will be 1 square plus 1 square, so it's 2, right? So my potential function will drop by 6. So this is catching up slowly. Okay. Anyway, let me jump. So yeah, so this drops by 6, but if I send the purple job to the first configuration, it drops by 8. So that's what I would do. I send it to the first configuration. If I can execute matches, I do that. And this is a greedy algorithm. And this sort of gives the boundary grid that I was showing you earlier. Questions on the algorithm itself? Okay. Exactly, yeah. So it may not also decrease at any point of time. Correct. Yeah. So here's just like one plot to show you that this algorithm works. And this instance also says what goes wrong with the naive greedy algorithm where if there's a match that you can execute, then you always execute it. Okay. So this example I've borrowed from this paper. So what's interesting about this example is that there is one configuration which has a very high reward of 100, and it uses 4 resources. Okay. One of those resources is this lambda 1, which arrives very slowly. So if you look at the rate at which all the other resources arrive, this kind of arrives very slowly, right? So it will be very rare when this resource is available. But this configuration also uses these other 3 resources. For example, this resource 6, which is also involved in this configuration, which has very slow, which has small reward. So if I run the naive greedy algorithm, where if there's any match I can execute if it's possible, what will happen is that this type 5 arrival item will make sure that I sort of very rarely have the item of type 4 available. This 3 will make sure that I sort of very rarely have item of type 2 available, and this 7 will ensure that I very rarely have this item of type 6 available. So when this sort of 1 arrives, I don't really have the other resources available to execute this high value match. And that's why this naive greedy doesn't work. And what I have to do is when these items of type 6, 2, and 4 arrive, I have to commit them to this configuration so that they can be used to match later on. That's really why commitment helps, but not like clearing as soon as you arrive. Okay, and this is basically the regret. So this blue is the regret of our algorithm, which remains bounded as time goes on. Okay, all right. So this is sort of just proof by example. Let me spend like 3 minutes going over broadly how the analysis works. We've seen like elements of this in Professor Iyengar's talk this morning, so this should be fairly straightforward, right? So as is typical in these kind of problems, what you want to do is you want to sort of create some potential function which tells you how your queues are growing. So the first step here is to say that if I want to study the regret at any time t, I can express that in terms of my current queue length. Okay, and in particular, I can write it as my queue length times the dual to my static planning problem. Right? Remember, the dual stood for the value of the resources. So in some sense, this is saying what's the value of the resources which I have accumulated in my queue. So that sort of says that if I can bound my queues, then I can also bound my regret. And to bound the queues, a natural function that you would like to study is the square root of this sum of squares thing that we defined, right? So this phi function had q squared. So if I take the square root, then I'm bringing back to the sort of size of q's. That's the function that I want to bound, right? So in some sense, there's a random walk psi. I want to say that random walk doesn't become very large. Okay. So a few things that I want to say to study this random walk is first that I want to study what are the step sizes. So here we can prove that the step sizes are constant. Again, because it's on the order of queues, my queues can only change by plus minus 1 in some sense. So the steps are bounded. What's more important is I want to say that if this random walk becomes very large, then it comes down very quickly, right? It has a large drift. This is where this general position gap condition helps us. So what this GPG condition gives us is that if my function becomes very large, then there is some special item that if it arrives, then my function drops very, very quickly, right? So this drops, and I can decompose my distribution into this item and the rest, so that if an item from the rest of the distribution arrives, then my function doesn't change a lot, right? So from this distribution, my function doesn't change a lot, but the special items will arrive with at least probability epsilon, my function drops a lot. So overall, if my function becomes very large, then I have some drift, which is sort of typically enough to bound my random walk. Okay. So again, this is something that Professor Iyengar also said this morning. If people remember Professor Iyengar's talk this morning, then he mentioned that there's a result of Bruce-Hayek, which in this case allows you to bound the queue length. But Professor Iyengar said that uh, the way the result of Bruce-Hayek works is that this drift condition gives us a bound on the generating function of the random walk. Okay. The tricky bit with using that result is that just with the drift condition, if you get a bound on the generating function and then say, what does that bound imply on the expected value of my random walk? That will imply 1 over epsilon square bound. And the reason is because an MGF bounds the tail. And you can't really bound the tail any tighter than 1 over epsilon square. But I just want to bound the mean. So what we do in this paper is, instead of using the result of Hayek, we say that, sort of show that if you have this condition, then you can also upper bound this random walk in the increasing convex order by a very nice random walk with IID steps. And IID step random walks are very easy to study, and that gives us this 1 over epsilon bound. Okay, so that's sort of something that's again new, which I haven't seen in other papers. Okay? And that sort of completes the analysis in this case. Any question on any step of the analysis? I know maybe this was too quick. Yeah. Yeah, probably it will still go through. Yeah. But I mean, the reason this helps is, so when I want to prove this drift, I want to, typically what you do is you sort of create a suboptimal policy, you study its drift, and then you say that your policy only has sort of more negative drift. Now our policy is using this potential function to make its decision. So it's sort of natural to pick that as the potential function, because it's easy to say that our policy will decrease it faster than any other policy. And Professor Iyengar did the same thing this morning, which is he also had a policy which was greedy with respect to the Lyapunov function, and then argued that therefore you have a negative drift. So that's why it's just natural to study this. Good. Other questions? So I think given the time, let me not discuss the other things I was going to say. And I'll just stop here. I'm happy to discuss things offline. I mean, there are like a few future directions, which is, okay, I haven't discussed what AQ systems is, so I will not discuss that. One interesting direction is that I assume that these jobs are infinitely patient, right? And Professor Iyengar was studying jobs which can also leave the system if you don't match them quickly enough. So incorporating these resources which can either leave or come back once you've matched them is interesting. There's some sort of non-stationary directions that I'm also looking to study. Okay, so yeah, let me stop here and not torture you further after lunch.
Any questions?